Yeah, and welcome to the Friday seminar. Okay, welcome to the Friday seminar. Today we're very delighted to have Professor Hani Mahmassani from Northwestern to speak to us. Hani does not need a long introduction because most people in the intro position know him, but for the benefit for our newer graduate students, I'll do a quick reduction. So Hani is the Patterson Discrete Chair Professor at Northwestern, and also is the Director of the Transportation Center at Northwestern University. Hani's research encompasses a very wide range of topics. I rather see which ones are the right question, which one he doesn't do. It's hard to find out. You know, it's so also Hani has been very active in the community and being the editor-in-chief of Transformative Science, and was the chair for the network committee and traffic flow theory committee for Transformative Research Board, and also has won many awards. And I think among the two of them I would like to mention is one is the AAE and the other is the Robert Herman Life Achievement Award. I think that means very special to Hani for that award because of the namesake of the award is a dear colleague and mentor. Yeah, and Hani has many connections to our campus. He served as on the board of directors for ITS for many years, and also a personal connection. His son was a TTP alumni. Yeah, so many of you. And my personal connection with Hani is through his student, Professor Jayakrishna at UC Irvine, which I took most of my transportation courses from, and I think that time is fairly new. A lot of the notes are from classes he took from Hani. Without much ado, let's welcome Professor Hani.
Thank you very much. It's a pleasure to be back in Davis, and it's wonderful to see the room full here. That's great. Thank you very much. I do not work on engines. I do not work on pavements. As Michael mentioned, I like the program so much that I encouraged my son to actually join the program, and I'm grateful to his professor, David Bunch, who is here now, from whom he learned a lot, and he continues to put that knowledge to good use in his current position. So today we're going to take to the skies, and we're going to talk about urban mobility as well as urban congestion, but we're going to see how essentially a new generation of flying vehicles, primarily vertical takeoff and landing, small aircraft that are electrically powered, might contribute to the urban mobility picture. And my own involvement with that was fortuitous because like everybody's like flying taxis, really, you know, I mean, are we seriously gonna do research on that? But what happened was I was at a conference in the same session as someone from Uber at the time when they had Uber Elevate, before they sold it to a company called Joby that is actually producing one of these aircraft. And at that conference, the Urban Elevate gentleman who had a degree in operations research was presenting their view, their business model, and was presenting some of the analytics they were beginning to work on. And of course, they were interested what might the demand be for these services. You know, they had conducted stated choice type experiments to kind of see the value that people might place on the convenience that it offers and so on. And I talked to them after, said, you know, we have tools. We can because they were also envisioning it, and I'll talk more about that, more as an urban, almost like a transit form of transit. that it would be at scale, it would move a lot of people, and it would be affordable. Okay, they were not positioning it as a premium, let's say, limo ride to the airport, but more as urban mobility, everyday type of travel. And so clearly they had expectations of both costs of production and service and so on, as well as demand levels. And those trips would have to be kind of multimodal because there's a last mile problem that may be involved with that. Like we have a tool, we can do a multimodal network assignment where like the long haul link could be by air, for instance. And we started talking, it just said, no, we're interested in something else. We want to know what might be the latent demand. And I said, we've done that before, and we kind of proposed an approach to them. And so we collaborated with Uber Elevate for about a year or so, estimating latent demand in the LA area. That's not what I'm going to talk about today. But mostly what happened then, my students saw that topic, and that's all they wanted to work on. And so I've had now 3 different PhD students who have gone through and they want to work on urban air mobility. So there's a lot of interest. And of course, the technology has been developing since. So there is we're conceivably within some form of deployment, not mass transit type deployment, but some form of deployment. And so what I'm going to talk to you about is what are some of the sort of service supply models, what kind of services might be envisioned. But I'm going to then kind of go back to the congestion part of it, because part of the vision is you go to the air, of course, you have that much more space to maneuver in instead of just staying on the ground. And so all the vision that the promoters tried to give, of course, is that congestion on the freeway will just disappear, right? Because you have all levels there in the sky to work with. And so we asked the question, will this really solve congestion problem? And we started examining what happens in the sky. How congestible is in fact the sky? And when you look in 3D, what kind of congestibility do we have? And the results are, surprising in one level, but they're not that surprising to understand traffic flow theory. One further comment, the art, okay? This is generative AI, DALL-E, that generated those, of course. So it's really, we say Hani and DALL-E when we give credit to the art. But you give it enough instructions and iterate and so on, and then you start getting stuff that may be somewhat decent. So you can get it in retro style or sync wave, or you can just ask for a watercolor with people and bicycles. And figured I'm coming to Davis, I should have, bicycles in my art, right?
Or you could just play film from the Jetsons.
Well, I'm sure that's in their database. Yeah. Okay. So I'm going to just again introduce the domain here, the territory, talk about service concepts and business models, and then go directly into airspace congestion. Looking at fundamental diagrams, any of you who've had Professor Zhang's class, of course, know about fundamental diagrams. So we're going to revisit those. But we're going to introduce a mechanism that really explains the emergence of fundamental diagrams. And that mechanism is conflict avoidance. So we're going to talk about that here. And that's kind of the new part from a traffic standpoint of the work. And then we're going to ask the management question, how do we structure the airspace eventually for some deployments at scale? And that kind of, think of it as like having an infrastructure in the sky, though it's all virtual, of course, but it's delineating various routes and so on. And we'll examine the relative effectiveness of those through the fundamental diagram concept that we will be presenting. Okay. And so the vision for urban air mobility is that it would be an on-demand, multimodal trips where you have both ground, of course, for first, last mile, coupled with air, that it would be deployed at scale. You would leapfrog congested arteries. It would improve regional accessibility for outer communities, though it would also probably encourage more sprawl, which is not necessarily a desirable outcome, trade-offs here. And there would be significant travel time savings at again, the vision was to have significant travel time savings at comparable price to ground transportation. So if you compare it, let's say, to rail transit, which would achieve savings in travel time, that might be, and if you can kind of bring it to the same price point, that was part of the vision. Okay, and so there's over 20 companies that are very directly involved in developing, the aircraft, but also in kind of thinking along the lines of business models for providing service. These companies go from, sort of smaller ones, and so Joby is one of those. That's what the company that bought Uber Elevate, along with all of the experts that were working in that area. But now, and then you have various startups like Lilium, Volocopter, Kitty Hawk, and others. And of course, you have the big players, Airbus and Boeing are both very much kind of in that space. And in fact, Boeing has acquired Archer Technologies, which is, again, developing tools in that area. And you've seen different images of those. They typically have multiple rotors. Some of them, you start vertical and then they go horizontal. Others have multiple types. There's different designs there. You tend to have 4 to 8 different rotors there, and these are envisioned to be electric. From a kind of carbon impact standpoint, they would be, unlike sort of the jet fueled aircraft, right? But that also raises questions on battery technology and charges and all of some of the same questions that we're dealing with on the automotive side. And in terms of sort of number of passengers that they would carry, the payload typically goes from 4 to 6, potentially 8 passengers that one might carry at the same time. And of course, there's all kind of trade-offs there. The original vision, in fact, was that Uber Elevate had, is that they would be, in fact, operating by 2025 at some level, with by 2028 kind of scaling things up. That's not happening, of course, and everything got pushed back, but the aircraft are now a reality, and we're beginning to see testing of some of these aircraft. The service is not imminent, but there are various plans. And so, as we had been sort of working in that space, the state of Illinois got interested, surprisingly, in what might be sort of a strategy for the state of Illinois related to this area, which was kind of visionary, because the state of Illinois is not California, and they are not always first to the table with these kind of concepts. But somebody was actually wondering given the importance of the aircraft industry, in the state and aviation and so on, they were asking, what should we be doing? And so we had this project for the past couple of years, and we're just about to release the final report that does kind of an overview of developments in that area and kind of trying to predict what impacts and implications might be. And so one dimension was that you can view, and they're calling it advanced air mobility, because the focus is not only urban. And so you can think of advanced air mobility as a mode or as a tool. And as a mode, it could be for people as an urban air mobility, but also, of course, for freight. Not just drone delivery, but kind of more sizable movements of freight. And as a tool, there are agricultural uses, there are infrastructure uses, and there's emergency services as well, for when you have disaster areas, response that you cannot access, and so on. Some of these really already have helicopters kind of in that space, but this is envisioned to be much less intrusive, safer, less expensive, and so on, and much more readily available. You look also in the agricultural realm, for instance, there's extensive use of remotely piloted drone, for instance, for fertilizer and insecticides and all kinds of stuff. And so we examined this from the supply side, demand side, looked at various business models, evaluated the externalities, and then came up with various policy regulations and so on. I'm just kind of advertising it because the report is going to be shortly. And mostly again, when you, part of what we had done was talk to a lot of the stakeholders, from an industry side, from an operations side, and so on. And there's different players who are looking at that. One of the things we learned, for instance, is that United Airlines is very seriously considering what could they do with this, and they're very seriously considering it for regional service. The 2 hour, 3 hour type, the 1.5 hour, the 300 mile, etc. trips from, say, Chicago to Springfield, which is the capital. And that would be like LA, San Francisco, potentially. It could be to Sacramento and so on. So a lot of places where they're now running bigger planes, they're thinking this might make a lot more sense for them. It would be cheaper, and it could eventually even be on demand instead of being regularly scheduled. So they're seriously looking at that in that context. Our focus has been more on urban and regional service. I mean, regional as a metropolitan, rather than between cities in a state or nearby areas. And so in our analysis, there's different elements that one considers in this system. You have the aircraft. There's infrastructure that primarily from the standpoint of landing pads and where you take off and where you land, where you locate those. There is the question of service coverage. If you're designing a system, how large of a network are we envisioning? And then what kind of fleet is necessary to provide that kind of service? How do we deal with first and last mile operation? Do we integrate the two? That was Uber's vision right there on your app. And in fact, they did a test at one point in Manhattan. They were flying helicopter to the airport, and it was right on the app, and you could get that. That was a way of testing how much are people willing to pay for that kind of service. Then questions of sharing the ride, because yes, it could be private, but ultimately, as we're seeing with TNCs and so on, sharing is caring, of course, and you can reduce costs, reduce impact, and so on. Then elements of the service, what kind of time window, for instance, for a do you have reservation with time window, or do you just do it on demand when you're ready? You just hop and get on one, and this is looking at it more from a sort of an OR standpoint, request acceptance and rejection. When you're operating this in real time, you may not be able to take some requests and so on. So I had a PhD student who focused actually on these questions, and ultimately what we ended up working on, we developed a simulation platform to evaluate these service concepts and operations strategies. We developed the OR for real-time optimization of the service. And so pretty much building on work that had been done both on TNC type dispatching as well as on trucking type work that we had done in the past. So that was all adapted for this application. Looked at market potential and demand assessment under different service assumptions. And then a lot of flux modeling, looking at airspace capacity, delay, and 4-dimensional fundamental diagrams. Looked at business model in terms of service design, demand assignment, and then questions of terminal, skyport location, and network design. Where we have accomplished the most are in items 1, 2, and then 4, particularly in 4, where we've had 2 distinct dissertations that have kind of filled some of that space. And so in my presentation, we'll talk a little bit about dispatching strategies, but then mostly go into flux modeling and airspace congestion. The first one was part of dissertation of Hani Ali Ahmad, and the second one was with Christopher Cummings, who is now actually working with United Airlines on some of these problems. Okay. So there's 2 main service concepts that have been under discussion. One would be a skyport model, like Uber Elevate was considering a skyport type deployment, where you have a finite number of terminals that are strategically located along the area. Then you have air service between the skyports, so you could have some transfers potentially. And as a way of consolidating the demand with an intermodal air and ground service. In some cases, you just stay in the vehicle, you don't get in the aircraft, depending on your trip. Other times you will mostly use these skyports. And so that was an example in the LA area. If you were to locate 10 of these skyport. They're really vertiports is what they're calling them. They're fairly massive, and there's up to 300 sort of transactions per hour that may be taking place there. So they're very intensive kind of operation. And what you could see here is this was based on our analysis. If this would be the origins and destinations that it would make sense to serve through that particular network. And then, of course, if you go to 15 vertiports, you can serve more. Part of what this is considering is really the access time, because in LA, of course, there's congestion, and then in some instances, it takes a lot of time to access the vertiport. So unless you distribute them, more broadly, it's not going to work that well. The other service model is ubiquitous service, and I call that the Dubai model because in Dubai, every building has a helipad on top of it. And so the vision is to go point to point. With point-to-point service, there's no access time, and that's your flying taxi kind of model. And so this is the same area. If you could do point-to-point, this would be the demand that you can serve compared to what you could do with 10 vertiports, okay? That would be consolidating the demand. Of course, in this case, there would really be no sharing directly unless there's a group that's traveling together. When you have big buildings, there may be more people that may want to travel together, but that's kind of the notion of coverage that you might get with that. And again, what this is considering with the vertiports is primarily once you take the access time, the time to get to the helipad, get in the aircraft, land again, get to your destination, what is the saving that you might get over highway driving, pretty much, okay? Okay, and so we came up with a third concept, really, which is a hybrid concept. And that actually was what Hani came up with. And she said, why not just do neighborhood level launch pads instead of, so it's not like it's not point to point, but it would be neighborhood level. So much more coverage than the 10 or 15. These would not be massive, so they're not gonna have the same impact on those neighborhoods. There's gonna be, you identify locations, maybe the top of, parking garage in some, an area. And so the idea would then be to have neighborhood level launch pads with demand consolidation and shared drives, because that's what really she wanted to accomplish, was to get more shared drives, but kind of maintaining some of the advantages of the the point-to-point service. And so you'd have a higher density of launch pads than a Skyport hub network, but then better vehicle utilization, which would lower the cost. And as you can see here, that the idea is there will be a choice of which launch pad a particular customer might go to. And this is part of the flexibility that the operator then has to match riders. So it doesn't have to be necessarily the closest one. You can take them to one that's a little further, but then get a few more people to ride together. And this all has to be done with very short time windows because it's envisioned to be on demand. And so she built the OR to do that. And it's a vehicle allocation routing type problem that will, I'm not gonna get into right now. All right. And so then we go back to the business case here. If you have a certain service network, how sensitive are costs to different elements, features of the service? What kind of level of service then can I offer users with a given fleet of aircraft? At what level of demand is the service going to be self-sustaining or profitable? And then how do we position the service? Premium service, special occasion, or everyday mobility like a TNC? And these are all still, pretty much open question. What we wanted to be able to do was to have the tools to evaluate it, mainly given fleet service, etc. We wanted the OR to be able to say, this is how many I can serve, and this is the kind of capacity that I would be getting from an assignment standpoint. And let's go over quickly here over the simulation tool that we had developed to evaluate these kind of questions, and then trying to emulate the dispatcher operation, fairly detailed dynamic type of optimization with a rolling horizon, where you have the network, the fleet, requests, new requests that are coming in, and we kind of emulate what the dispatcher might be doing, and that's a whole other talk. All right, so some of the main takeaways from that, kind of skipping because I really want to get more into the flow modeling. So that demand consolidation could in fact significantly decrease the aerial mileage per request and also increase the number of service requests, which in turn increases the total travel time savings compared to ground-based transportation. The effectiveness of the demand consolidation scheme is dependent on the demand pattern, whether how dense versus sparse it is, and the pre-specified level of service, that is the maximum delay that is tolerable before you actually embark on that trip has a significant impact of the number of rejected requests. So there's quite a bit of sensitivity to that particular factor. And this is all based the analysis that Hani had done. So the next part here is if any of you are interested in that side of the work, I didn't want to get into it because it's really elaborate formulations in terms of the optimization side of it. And it's hard in 15 minutes to convey all of that if one doesn't have the full background. Whereas the flow modeling, I think, is much more reachable. And frankly, we've done a lot more interesting work, in my view, on this side right now. But if any of you are interested in the kind of service model, the real-time dispatching and so on, if you have a couple of papers, I'd be happy to share them with you. Okay, so the question here that came up was, so what happens in the sky? Is it really not gonna, is there that much capacity that we could sort of deal with all of that demand? And so that brought us to this notion of, well, we really didn't know when we started looking at that. And some of the motivating questions, as I said, were how congestible is airspace compared to highways? Does adding a third dimension solve urban traffic congestion problems? What might be a practical capacity for such systems, and where is the bottleneck? And what is the effect then of different spacing requirements between aircraft, horizontal and vertical? And what is the effect also of the maximum speeds of aircraft? Does that really change kind of the flow patterns that emerge? And so, we thought that as urban air mobility scales up and as more vehicles to the airspace, operators and regulators will need an understanding of air traffic flow. And the image that I have here, this is a rendition of what of these horrible vertiports would be looking like. They would be massive structures, and that was in some of the early Uber Elevate kind of visions. And you don't want that in your neighborhood, right? But that's what's kind of the model that they had envisioned, and that, then they hired top architects to design much better looking and integrated kind of vertiport. But that was like one of their initial sort of proposals. Okay. So some basic concepts here in aircraft routing. There's different types of routing through airspace. Basic flight would be no routing restrictions, and the aircraft are responsible for self-separating. Basically, that's what birds do, right? They figure it out, they manage their conflicts. You can have, the other one is free route, where there's no routing restrictions except for advice and deconfliction from an urban traffic manager. Or you could be in corridors. And so this is an example here where it is, you have just essentially basic flight, there's no restrictions. In this case, there is some controller that's kind of giving information for deconfliction, etc. But it's still, you kind of choose the route. A more restrictive one is when you have corridors. You define corridors to the sky, and this is where the aircraft has to stay. And think of them as tubes, or that are going through. Or you can have fixed routes. And so this is where, if you have system optimal routing on highways, for instance, you determine for each aircraft what route they should follow, and there is a central controller that is providing these fixed routes. And this gives you an opportunity to manage, best. Whereas, of course, this is much more flexible and it becomes much more decentralized. This is a lot easier to sort of manage, if you wish, from a central control standpoint. But then, if you're really scaling up, it becomes more difficult, and the likelihood of the likelihood of conflict increases. Whereas in this case, you can kind of manage it as a controller. Okay, so less restrictive routing can also be more direct. but could experience more conflicts between aircraft, as it's scaling up. Whereas corridors and fixed routes may be useful for restricting over certain neighborhoods and other areas that should not be flown over. If you try to fly a helicopter in Washington, DC, it's almost impossible. Everything is sensitive. And in fact, we were trying to collect traffic data with the helicopter in DC area. Impossible. It was for Federal Highway Administration, still impossible. We could not do that. The only thing you could do was to sort of be on bridges and get traffic data, whereas in most other cities, we just fly helicopters for data.
News channels, they have their helicopters flew over like the Bay Area and reporting.
So, okay. And so there's been quite a bit of this, a growing literature on the sort of airspace management angle. But nobody had examined the congestion part, which is where we came in ultimately. And so there's been several new airspace concepts proposed to integrate advanced air mobility operations into the existing system. With Federal Aviation Administration has documents outlining concept of operations for these services. And part of what they're kind of proposing is you have different types of vehicles, different classes at different heights of session. And so your UAM corridor would be somewhere above the little drones that are flying, the little, maybe the one that may be delivering packages and things of that nature. This is where the more serious sort of urban air mobility vehicles might be flying. So they would be closer to 700 to 1,000 feet in height compared to below 400, which is then reserved to the for the smaller fry there. Versus, of course, and again, there could be multiple classes here of vehicle, and so they call it XYZ here concepts, where X airspace would be for low density rural area operations with the operator responsible for dealing with conflicts and so on. Y airspace would apply to low density operations above sensitive surface areas with only pre-flight deconfliction, whereas Z airspace would be high density with complex operations with various collaborative features between the vehicles. So that's the concept of operations version 1.0 by the FAA. And so when we got into this, so my former student, Chris Cummings, is very interested in this topic. He was taking my traffic flow theory class. They have to do a paper. And I told him, maybe you should build a simple simulator. And let's see what happens, what emerges, and that's what he did. Because my sort of notion was, we should see a fundamental diagram emerge. Because for birds, you can, for many species, we kind of tend to see fundamental diagrams. And I said, just, build a simple simulator and let's see what emerges. So he built a simple simulator to emulate these aircraft and then look at kind of how this, does it congest? Do we get a fundamental diagram? And can we then use concepts from traffic flow theory to examine this situation? And so in his simulation, he used a decentralized system of air traffic control, where each vehicle is scanning for potential conflicts and then resolving them individually. So his initial simulation was more like free flight with decentralized conflict resolution. But he did the conflict resolution in a very careful way, and he found in the literature a nonlinear programming formulation for that problem, where you consider what's around you and then you can optimize your position accordingly. Which means, simply speaking, is if you sense a conflict, and where the conflict is an important parameter in this. If you sense a conflict, you're either going to deviate, or you're going to go up, or you're going to go down. And so those are the maneuvers that you might do. And he started by simulating just 500 trips between 38 skyports over a 2.5 hour period. And in the assumptions he made is that vehicles have true vertical takeoff and landing capabilities. He assumed them to be able to fly at up to 100 miles per hour horizontally and 25 miles per hour vertically, which is within the range of what industry tells us we would have. Then he did sensitivity to all of that. The minimum vehicle spacing was set to 30 seconds of maximum velocity, which is about 1.3 kilometers horizontally and 0.35 kilometer vertically. Okay, that's when you translate them at the maximum velocity of 100 miles per hour. And vehicles were given an initial altitude to fly at, but they may deviate to avoid collisions. So everyone goes to some level, and we had discrete levels to which these aircraft were going. And so I can show you what the simulation looks like. Okay, so this is from this is the top view, and again, you can, the blue squares are the vertiports, and so you have travel between these vertiports. This is a top view, and then you have the you have the side views here, and this is the 3D view that you could see there. And so you could see them, going up to a certain level, and in some cases they will then, they drop down to go back to their destination. And in this case, it's still not getting too congested, but let me move it a little faster. And you could see there's a lot of balls in the air, right? And you could start seeing conflicts that are forming, and you could see them slowing down also at some of these levels because of the conflicts that may be, developing. And we can have a little bit of bottlenecking that is happening in there. This is our first sort of set of simulations.
So for the vehicle, this should have a speed range, otherwise they'll drop down, right?
Yeah. I mean, well, they could hover.
Oh,
yeah, they could hover. There's no problem with hover. Yeah.
Person in space. They don't communicate, right? Or do they?
You're sensing the vehicles around you, so yeah.
So you're just dancing. I mean, there's no actual communication between the vehicles.
There is not much coordination. Well, there is coordination because we assume that there is kind of a central controller, that's deconflicting, but only among neighbors.
Okay.
Only among neighbors, not for the entire system. It's decentralized among neighbors. Okay. And so we then said, well, let's work with go back to our basic traffic flow theory here, right? So what we did is extended essentially Edie's definitions to 4 dimensions. Okay, so the original in traffic flow theory, we had 2 dimensions, which is X and T, right? These are 2 dimensions. When we went to networks, we had X, Y, and T. Now we have X, Y, Z, and T. And so this is why it's 4-dimensional fundamental diagrams and 3-dimensional space, but 4-dimensional fundamental diagrams. And in this definition here, so if you look at the definition of the average flow and the average density, it is extending Edie's definition, Leslie Edie, where to get the flow, it's the sum of the distances that are traversed by all of the vehicles over an observation period. So DI is distance traveled by vehicle I, summed over all the vehicle, divided by the dimensions, X, Y, Z, and T, because the vehicles can go everywhere in that space, essentially. And then to get the density, it's the total time, sum of the time that is spent by the vehicle. And in this case, our observation period is that, this is the X and Y that we're considering, but the entire depth of that. Okay, and of course, then you get the speed is just the average speed. This total speed divided by n. Yeah.
So Hani, you have 2 speeds. Q divided by K would be the total distance divided by total.
Correct. You get the same thing.
Yeah, you
get the same thing. Yeah, exactly. But I'll get more to speed because then there is an effective speed, effective flow. We'll discuss that later. So initially, and then we verified, of course, that Q flow rate is the product of speed and density. And so this is the product, this is flow rate, perfectly aligned. So it verified the fundamental identity of traffic flow. It's good. The first test, it's like, show me. But if you can't do that, then there's something wrong. So align. And then we get our flow versus density. And sure enough, typical sort of behavior with the hysteresis here. To get the congestion, and it's like, oh my God, it's like a freeway. Same behavior as a freeway. So that was how we got started in this, and we did multiple runs, and they were all kind of showing us this sort of the same thing. And then we varied a few elements, and then you plot the speed versus density, again similar pattern with kind of the hysteretic part that goes on the other side. But that was a starting point. We said there's got to be a way to sort of do better theory, than, because this is something that emerged empirically. And so Chris went and started looking at a gas theoretic model, okay, because these are like particles of gases essentially. And so he built a theoretical model where so vehicle density creates conflicts. That's the starting point, because more vehicles in airspace increase the chance of conflicts for each vehicle. Second, conflicts decrease the effective speed and the actual speed. So effective speed is the speed in the direction that you need to go. So if you're going back and avoiding and all of that sort of stuff, that's a reduction effect in your effective speed. So it's a directional speed basically, because conflict resolutions involve one or more deviations from sort of the direct trajectory. Also, the flow rate and the effective flow rate would be products of density with speed and effective speed. That's your fundamental identity. That holds also the effective speed. So the idea was to go from vehicle density, look at the impact on conflicts, try to quantify that, then capture how this reduces the actual effective speed, and then how that will affect your flow rates. And so your speed density is kind of going through the impact on conflicts first, and similarly your density flow relationship or your fundamental diagram. And so to illustrate that, another simulation, in this case he had them placed sort of in a circle, this is the top view. But essentially he did a bunch of simulations where he was measuring the conflicts. Okay, and so you could look at this here, and you see that as these densities are increasing, the conflicts are increasing. So he found some interesting work that used a gas law model for predicting conflicts in airspace. And essentially, it works by estimating conflicts in the airspace in front of each vehicle, where C is the number of conflicts, D is the separation distance within which so if you're within that distance, then you have a conflict, so you have to maintain it. So if the separation distance is large, there's going to be effectively more conflicts being diagnosed, because there will be more likely to have a vehicle in there. And so the conflicts increase with the separation distance because they catch more other vehicles in there. It depends on the vehicle speed, the square of the vehicle density, and the look ahead time within which you're determining if there's a conflict or not, and the airspace area. Again, the larger the look ahead time, the more likely it is you're gonna declare a particular vehicle a conflict. And then A is the airspace area. And we counted the conflicts as a function of density, and sure enough, these are the simulated points, and this is the theoretical relation. Very nice R square, and we then estimated the points with that formula, with the given separation distance, etc. And that's what we got. So that was pretty nice fit. And this is what you would expect, that the conflicts increase non-linearly with increasing density, because you have
The red line is given by the formula.
correct. Yeah. It's the one we estimated according to the formula. And so then he you can go from that then to how it impacts the speed. And so then the speed, the average vehicle speed is negatively impacted by conflicts. So you have Vmax minus the number of conflicts times a constant B divided by N. And here B is the speed loss per conflict, basically. So C is, the number of the number of conflicts as predicted by that relation. And so using conflict count here, you plug in the expression for conflicts and you get a relation between the average speed and density and the separation distance again. And that illustrates the relation between average speed, maximum speed, separation distance, density, and conflict resolution. Vmax is the maximum speed there. All right. And so you can do a similar thing for the effective speed, where effective speed is the speed in the, again, so the direction of travel. And you could then start, this is now the theoretical models that you obtain. And so for you, depending on the separate spacing requirement here, you get different conflicts versus density, where you have the fewest conflicts when your separation distance is small. As you increase it, increases with that. And then you look at the speed versus density, it's the other, it kind of reverses, right? And because you then will have less of an impact on speed when you have smaller separations. You can similarly look at the effective speed versus density, same relation, just different numbers. And then you can look at the effective flow versus density, and that's your fundamental diagram right there, as it is impacted by the separation distance. So you have the least capacity when your separation distance is large, you have the highest capacity when your separation distance is small. Okay. And this is now taking the simulated results, because we did a whole bunch of simulations under these different values and so on. And sure enough, you could see again how that varies with the different spacing requirements, with the largest spacing giving us the most reduction in speed at a given density. And when you have short separations, of course. So basically, you're not seeing more observations beyond this density level when the separation distances are greater. And this is effective speed versus density. And again, looking at effective flow rate versus density and speed. Again, with the very large separation requirements, you're just not getting very far. But in all cases, it's still a similar kind of pattern as we have for our highways. This is effective flow rate versus density for different maximum speeds now. And so, these start intersecting here, and you can see that with higher maximum speeds, you are reaching higher capacities, but then not able to reach necessarily the same densities, because within the same separation, at a higher speed, you're going to catch more distance.
So those are vehicles flows per minute, or
this is this would be these are per minute.
Per minute.
Yes. All right, so see here. Okay, next I'm gonna talk about how do we manage this process ultimately. So we're gonna look at some network architectures and air traffic flow, kind of applying these concepts and using that simulation framework that we have. In the interim, we had run what is the impact of restrictions. We started putting bottlenecks and restrictions here and there and so on. And then from that, he built a tool to evaluate different network architectures. And so some structures, such as geovectors, which basically give you a direction in which to go, corridors, restricted airspaces, can be combined to create different network architectures. For example, an unstructured network versus a network of corridors. Then these are applied to get the network level and looking at measures of travel time, travel distance, conflict rate, capacity, etc. And so Chris built different network architectures and simulated them to explore the broad impact of these structures. So he considered 4 architectures. One is unstructured with no restrictions. Geovectored network where you have heading restrictions by altitude level. Free route corridor network. So these are regions of unstructured space that are connected by wide corridors. So you have freedom of routing within them, but you cannot, there's restricted areas. And fixed route corridor networks. This is where you have to follow a fixed route that's given to you, no freedom of maneuver. And those were evaluated using 7 broad impact measures: trip distance, travel time, share of available airspace, network capacity, conflict rate, concentration of conflicts, concentration of trajectories. A fairly elaborate evaluation. But this is what these network layouts look like ultimately. Unstructured, you could go from anywhere to anywhere. Geovector, you're putting, in this case, you're grouping essentially headings on the same level. So it's like you have one-way streets basically. So you put them on the same level if they're going in a certain direction. So that's why it's geovector. And it's mostly you're doing that using different levels. Okay. In the unstructured trajectories, we also had 4 layers, but you choose it randomly. It's not predetermined based on your heading, as it is here. The free route corridor, so you restrict certain areas, and that leaves certain passages that you can do. So this is, for instance, if you want them to go only over freeways, or over, that would be kind of what you would get if you were replicating the freeway corridors in the sky. It would look something like this. Here we had only 2 layers, and the restrictions, form these wide unidirectional corridors. And with fixed route corridor trajectories, we did that in 2 layers, but then again, your full route is predetermined. You can only follow that route. Okay? So it gives you more control, certainly from a management standpoint. So looking first at the conflict rate and capacity. So this is, here we go from unstructured to geovectored to free route to fixed route. And what you're gonna find is you're getting, at a given density, you're going to get more conflicts when it's unrestricted. You're going to get the least conflicts when the routes are all fixed by design. And then geovector being, better than unstructured, but still not, a little closer to having more structure. But when you look at capacity, the free route can cover a wider, essentially can scale up. The fixed route, can scale up more in terms of reaching higher densities, but you're getting, at lower densities, you're getting the highest capacity with the with the unstructured and the geovector. And so geovector would be somewhat better than, because for the same capacity profile, fundamental diagram is giving you less conflicts. So that would be more desirable. What does not work very well here are the free route corridors. They're giving you low capacity, and from a conflict standpoint, they're not doing that well, and they don't scale up much at all. So those seem to be less desirable. And looking at travel time and trip distance, this is in this case the travel time in minutes. In these different situations, free route corridors also seem to have like the worst delay perspective, with the kind of the unstructured and geovector dominating, but only up to a point in density where the fixed routes will then take over. Okay? And if you look at the distance traveled, though, the fixed route corridors have the most trip distance, because you're fixing all the routes there, less ability to take advantage of things, and both geovectored and unstructured seem to do quite well in that regard. Free routes increasing there. And if you look at the concentration of conflicts, so a structured network is going to have conflicts everywhere by the way it's configured, but geovector, as we saw, will have fewer of those. The free route corridor will have a lot of conflicts where in the corridors themselves, and with the fixed route, they tend to be most distributed essentially. So implications: congestion is the large negative impact on user experience, travel times and distances. In congested conditions, travel times could double on some networks, while trip distances can increase by 25%. Moral of the story: there is no free lunch. But there are ways of reducing sort of that impact, as there are ways of reducing it on the ground as well. But that's not going to be the panacea that it's essentially promoted as being. The vertiports may artificially concentrate aircraft and conflict. So I tend to not like the vertiport concept because it's really kind of creating a whole set of issues. It's going to be a problem on the ground. It's going to be a problem in the sky. And so they're really not that great as a concept. So our hybrid kind of neighborhood distributed one seems to be a better concept. And so because as we saw there, the conflicts tended to be near the vertiport, which is where those were located in these fixed, where you had restricted areas. Unrestricted networks offer routing efficiencies, but restricted networks offer lower conflict rates. Geovectored networks offer the same routing efficiency as unstructured, but with fewer conflicts. And free route corridors offer greater routing efficiency, flow densities, while fixed route corridors generated fewer conflicts and reduced congestion. So conclusion, as I said, no free lunch, but certainly an area that is very interesting from a research standpoint. And so now one of the things we're doing is we're doing DKA in the sky, basically, because you can assign where they could go in GeoVector, for instance, if you have different levels. So what do you do when you're predicting a certain number of them? So you get into sort of real-time route assignment. You can also do some scheduling of when you use the different levels and things of that nature. So that could be fun as well. Demand questions, wide open at this point. So that's why we, in fact, chose not to invest too much on the demand side other than ranges. So when we did some demand projections for Chicago area, and it ranged from 0.8% sort of trips to up to 8 or 9%. Depending on prices. So under the most sort of advantageous conditions was hitting 8 to 9% of the total, which would be very significant because that's more than transit. But still that's very optimistic. More likely we're going to be in the sort of 1 to 3% and under reasonable deployment levels. But again, there's still so much uncertainty right now in that space. We didn't go too far in terms of studying that. At one point, as I said, Uber Elevate had done state of choice type experiments, but it's really difficult to get at that. They had a wonderful virtual reality representation, which would be great to kind of study how people react to it, but that would probably give more optimistic estimates because it's such a nice experience when you do the virtual reality. Of course, you're going to use it if you don't have to pay for it. Anyway, all right. Well, with that, I can take questions. I guess yes.
When you said bottlenecks, I thought of general aviation airports and maybe more specifically general aviation airports with crossing runways, as you got lower glide paths. You got to be out probably above 400, probably below 900 or whatever the vertical separation is. So you're out there, and not only that, you've got people on approach doing, I forget whether it's left wing or right wing, but they're treating it like around about, up around 1,200, 1,100, I mean, up to 1,000. And so.
Well, we don't have these issues here because there is no landing per se, other than it's strictly vertical.
Yeah, but when you're in transit in the general aviation airports, in your way, you had better go one way or another, and it's going to create conflicts if that's not structured.
I mean, yeah, there's avoidance of conflicts with large aircraft.
Yes. Well, and
That's not what I mean. That's in this idealization we were looking mostly at just the vehicles themselves.
Well,
but that's where the FAA is going to come in and regulate that aspect for us.
I would think that's still where your bottleneck's going to be, because everyone's avoiding.
Yeah, I mean, absolutely. That might be. I mean, this would be a region to avoid, basically. So it would be like these restricted corridors that we're looking at. From the standpoint of the eVTOLs, they would be restricted from those areas because of the potential conflicts that you mentioned.
Yeah. I'm sorry, this is how I looked at the grid. So, well, yeah.
So you used the phrase latent demand. I
Yes,
think in Davis, we would call it slightly different. We would call it induced demand. Two different words for the same thing. One sounds great on a business case. The other is terrifying when you study climate change and sustainability. And so I'm curious, because you alluded to the fact that you guys were looking at latent demand, like the congestion that you're showing here, what are the impacts? Like how many of these trips would be moved from our current congestion and make differences there potentially? And how many of these trips are trips that are new trips? And so essentially we're just gonna have 3D congestion at
yeah,
this
the
point.
answer is this work did not examine it, so we do not know.
Okay,
But there's another answer, which is in the work that Hani was doing, where she was kind of emulating how the dispatcher might operate in Chicago.
yeah,
She took all of the TNC trips in Chicago, because it's all published on a portal.
sure,
She took all of those and then she applied certain rules to them, which had to do with the kind of whether they would be candidates for this type of service. And I don't recall the exact numbers, but so we've done filtering of that nature. And in this case, there's no latent demand per se, it's just taking TNC as a way, as the potential total. So we're not removing anything from the people driving their own vehicles, only those who are using TNCs in that application, just to have reasonable demand levels for the initial types of service. But what I meant by latent demand was exactly demand that is not materializing. Induce is different than latent, because latent, you get it from a demand curve, basically. And on a demand curve, if you shift the travel time, you're gonna get more demand, essentially, that is gonna materialize. That's different than induced in the sense that somebody has relocated because now they can get there using UAM. To me, that's induced.
okay,
But the latent demand is the one that's not materializing, pretty much because the cost is too high, given their locations. So that's what we had estimated in LA, and also did that in Chicago. And in fact, what I showed you in that, the trip desires for the vertiports in Chicago included some of that latent demand that had been estimated, both actual and kind of, so this was looking at total potential demand that we had, but it's all crapshoot at this point. Don't know where it's gonna fall.
Tim?
Yes, Doctor, thank you very much for your presentation today. You presented today on the different business models when it comes to structured versus unstructured networks. So my question is though, has anyone, I understand we're in the preliminary stages right now, but has anyone considered analyzing the business model efficacy, the success rate of, depending on the speeds at which these UAMs will go, depending on the distances they need to put them, because it's essential to any future business.
Yes, and that's exactly what, say, Uber Elevate was studying. It's what's gonna be, how many people can we move essentially at what fare for a certain level of investment in terms of aircraft, in terms of infrastructure, and so on. And the model that I did not spend time on, they gave you that information because it was looking at how we may be deploying these aircraft to serve demand. And so that would be more relevant to the business model. This is looking more at one element of the business model that's going to be the travel time and then the airspace capacity. Just because we have that airspace capacity doesn't mean we're going to have it unless we have those vehicles that somebody has invested in and built and is using. So there's just, again, two sides to the story. And the truth is we haven't integrated the two yet because each one is sufficiently complex in its own right. So, good question.
Are these eVTOLs being designed to be autonomous? And if so, does that sort of open up traffic patterns that would be seen as sort of riskier if they were driven by people?
Correct. They are being designed to be autonomous. And in flight, there's in fact a lot of autonomy already today. Most large planes could be flying without pilots, and in fact they do. The pilot only intervenes in very limited situations. The initial deployments were envisioned to have a pilot, initially for people to be safe, but then, when elevators were first invented, there was always an operator that pushed the button. Eventually, people learned to push the button themselves, right? So it's to me, it's that kind of analogy in this case. And of course, that means then that some of the some of the more decentralized strategies, of course, would have to be carefully calibrated in that sense. But what we're seeing already with autonomous vehicles on the ground, which I would argue is much more complex, in fact, than what you have in the sky, because you have less infrastructure around you in the sky to sort of hit. Once you're above a certain level, you don't have left turns, and you don't have pedestrians, and you don't have bicycles, etc. to deal with. The autonomy seems to be already deployed at scale in some locations, like Phoenix, for example, without any glitches. Other places there have been glitches, but those were not Waymo vehicles, were other brands.
So how much are these systems disrupted by normal variation in weather patterns?
Good question, good question. The intent is for them to be robust, but then our jet aircraft sometimes are disrupted. Certainly helicopters are disrupted, but these are much more stable than helicopters, and they have much more redundancy than helicopters do. But the answer, we tried something to actually, we did one analysis to see how many days in Chicago could drone delivery work. And we can identify based on visibility, what's the precipitation, and so on. And you do eliminate a certain period, but that would be a factor. That would be a factor.
Okay.
Yeah. Yes.
Thank you so much, Mahmassani. That was a great presentation. One question about the use of UAMs for mass transit in the future.
Yes.
After doing all this optimization and everything, what was the system capacity that you're predicting for the future? Because you already know about the network structure, about the speed and everything. So do you think it might be a viable alternative in the long run between downtown and suburban areas, one way?
Well, here's the thing. There is no substitute for ground-based mass transit if you want to move large numbers of people where you have high densities. Okay? I mean, there is nothing more efficient if you're on,
Wait, Hani, say that again, please, just one more time.
It's very simple, right? There is nothing that's going to work there. And so this is not to move huge numbers of people downtown, though for some parts of the day. So this is going to be primarily in areas where you may not have that level of mass transit deployment, or you may not have the patterns that can fully support true mass transit. Okay? And I do not consider a bus that's circulating locally to be mass transit in that sense. So again, I'm going to go back to what Uber was envisioning ultimately, and they had envisioned scenarios where, and again, LA is not exactly a city where you have a huge reliance on mass transit. It's patterns that are so distributed and sprawling and so on. So in those environments, it could substitute for forms of where transit may be inefficient. But to go back to your numbers, we didn't go far enough, I think, in our work to have definitive answers to these questions. This is still so what we did is we built the tools that would allow us to answer some of these questions. We demonstrated the tools. We did it, run it in places like Chicago, tried LA, etc. But a lot more needs to go into this to consider the entire transportation system. We were more focused on getting that component right. And our next sort of step is to integrate urban air mobility as a mode within a multimodal network assignment tool that we have that currently will consider different forms of mass transit, different form of first mile, last mile, from bicycles to micromobility and so on. And this is going to be one additional mode. And with that will then give us a better sense of what it takes to run the entire area. But we do have the ability to say, for so many vehicles, this is the demand that we can handle. That's, that kind of sensitivity we already have using some of the tools that we've developed. And now we're getting a sense of what can we handle in the sky in terms of capacity. So, but we don't have yet that answer for you.
So this is really great work on how to make it happen.
Yes.
And I think a couple of our questions is it a desirable future? And any estimation on the, let's say, greenhouse gas per passenger mile, even so it's not the same miles while we're flying, or something similar that we can kind of start to estimate if it's a desirable future.
Okay, so there is no question that from a user standpoint, it's a very compelling proposition. It's very compelling, okay? For the, because we want to get there faster with less conflict, etc. It's a nice ride. Now, from the, so what really stands in the way of this might be cost. Not just out-of-pocket cost, but sort of the entire range of costs that it imposes. If you, now, to the extent that these are electric, then sort of the carbon impact is going to be limited, and then you go into the life cycle kind of question of batteries, production of electricity, and so on, that we're dealing with electrification of automobiles. So the problem is comparable in that sense, but it's not a pollution generating or a carbon generating type of mode because it's electric. So if we accept that electric is kind of addressing that problem, then that's meeting it. There is a noise consideration. And if you, so the studies that Uber Elevate had done, were comparing, they had this really cool video. If you go on YouTube, you might still be there, comparing it to what is this noise gonna be like? And they placed it similar to like having a river, like water flowing, based on the on measurements that they have done, and so they put it side by side to sort of compare it. They did it, I did not, so I can't speak for that. But that's sort of the noise part of it. Now these rotors tend to be quite, well, they're not very noisy. I mean, if you take your little toy, your toy drone, whoosh, and so it's more of that, but it's not a kind of really infringing. That's
another thing
pro.
with the batteries, right? I mean,
Yeah.
you don't have an engine running, you just have electricity. This should be better.
Exactly. Yeah, there is no. I mean, your electric vehicles are much quieter, of course, than their gasoline brethren.
I think also there's substitution effects for the general aviation.
Yes.
Right now there's a lot of this kind of flights, and this can replace some of them, will make them cleaner.
Yeah, so I mentioned that United Airlines is looking at deploying. I mean, their use case is for these flights where they now have the Embraer, jets and so on, the CR jets, to deploy this type of service between Chicago and Springfield or Milwaukee, or just a lot of these close-in areas where they're now running regular jets, and so that's both more economical as well as less environmentally damaging.
So we have one online question. Would you mind
Yes.
reading one question?
Yeah, so Ruth Fulton says that based on regarding slide 20 or in general, what about the impacts of large numbers of flying taxis on sightlines into the sky, or like noise experience on the ground? And these seems like really important questions.
Yeah, I think the noise aspect, I kind of shared what I know about it. There's actually another issue on the ground, which is some people don't want these things over their heads, right?
Yeah.
That might kind of argue for restricted spaces, but we do tolerate planes, whether we like it or not. But that's not going to be nearly as invasive noise-wise, but there may be more of them. Okay. So in terms of the sight lines, you mean for people on the ground looking up or the vehicles looking down, or both of these issues? Yeah, that's the question to the gentleman. Anyway, yeah, there's definitely a concern that you know, people are gonna be able to look, I guess. So if you're in your hot tub, you don't want to be looking.
Am I unmuted?
Yeah.
Oh, yeah, hi.
No, I think, yeah, I just unmuted it. No, I think we.
Thanks a lot for that, and I enjoyed the presentation very much. I'm actually next door because I couldn't fit in the room. And I appreciate that this was mostly about how to make this system work in the sky. I do think, I think it was Carrie who mentioned about induced demand. I think, you know, maybe our group would be a good group to look at what does this mean for travel more generally on the ground. And I think one of the questions is what percentage of different kinds of trips this could possibly carry. And if it's a very tiny percent, which sounds to me like it's mainly dealing with rich or business-oriented trips, then it won't matter much, but then it's not going to matter much anyway in terms of travel. We already have different kinds of aircraft to carry business travelers and premium travelers. If it is enough to matter, 5%, something like that, we are going to have induced demand, and you can call it latent demand if you want to, but it just means we're going to open up space on the roads for more vehicles. So you would have to take that into account in terms of a broader analysis of what impacts this is having in any number of dimensions. Thanks.
Yeah, thank you. These are these are good points. In terms of the demand, the report that I mentioned at the beginning of the talk that we just submitted to IDOT actually takes a stab at estimating volumes, et cetera, that one might get based on both substitution and new demand and so on. And again, the ranges that we're getting right now is fairly wide, from 0.8% to up to 8 and 9% in some cases of the existing sort of travel that we have. We've not we actually have also estimated, but only in kind of broad brush terms, what some of that latent demand might be, again, without going into new development type considerations that are inducing additional demand. But I think policy needs to be informed, I think, by all these elements, but also policy needs to invest in studying these questions as well. And policy is not fully investing as they should be.
Thanks.
Other questions?
One more. Yeah. Yes. Based on the different simulations and tools that you proposed, I wonder if there's like an ideal size of a city or like an ideal size of a metropolitan area.
I can't hear you very well. If you speak up.
Sorry. So based on the tools that you proposed, is there like an ideal size of a city where this system might work based on different constraints and optimizations that you want to look at?
That's a good question. It's not so, it tends to work better where you have larger cities, okay? Because that's where you get the benefits of the travel time saving. Because you have kind of a fixed cost of taking off and landing, right? That's gonna, regardless of the distance that you're traveling, that is gonna be incurred. So the more distance that you have to travel, you can amortize that takeoff and landing time better. And so that's what we've generally found, is the trips that are better served are going to be the longer ones. It's not surprising. And so larger areas will tend to support that better from a sort of purely sort of capacity and operation standpoint. But again, there's interest in it in more rural areas, frankly, in a state like Illinois, because that's going to give accessibility to folks who otherwise do not have it, particularly in terms of going to larger central places. And you could view that as maybe induced demand, but it's also an improvement in quality of life for some of the folks who live there, who otherwise may not have access to, performances in theater and what have you, and somehow, watching that. I mean, so for these types of applications, and they also view it as a way of, if you're trying to track businesses to locate there. So here's the other side to it now. With hybrid work becoming much more common, you do have a notion of these supercommuters who might rely on a mode like this for the once a week that they have to travel to the office. I mean, I was reading, I think in the Wall Street Journal about this supercommuter whose office location is in Denver, but he and his family decided to live in Des Moines, Iowa. And he flies basically 7 hours from origin to destination to go to Denver twice a month. Okay. And he continues, and then he works remotely the rest of the time.
The Bay Area, car commute is like 2 hours.
Exactly, that would be a perfect, yeah, exactly.
Sacramento region.
Same in LA area where, the more, so that's gonna lead or support more sprawl, but that's primarily induced by hybrid work. The fact that you can work remotely, that you don't have to go every day. And so that is another important trend, I think, that is part of the demand equation today.
And just one time in Alaska, we saw many backyards. Each backyard has a aircraft, small aircraft.
There are parts of Houston up north where the houses have places for their airplanes in the
Exactly.
backyard.
Exactly.
Every time we talk about this stuff, I flash back when I was a graduate student in Houston in the 80s. And all the helicopters going back and forth from different downtowns to the airport. It was a peak at that time because of the ratio of rich people to the cost and whatever. And we're just talking about a slightly different version of that, I think.
There will be a demand, is how we manage it, I think.
Yeah, I'll give you another example. From Nice Airport to Monaco, Monte Carlo, is a 6-minute helicopter ride, or it's an 1.5 hour car ride, right? And so there is regular helicopter service. This would be a much more comfortable ride than of course, that's again more of a premium type of that type of travel, and that's maybe where it's going to start. Where it's going to deploy initially, most likely we're going to see it in Dubai, because their regional transportation agency, which also runs transit, has taken this on. They want to run it. So that's one, and they're investing in technology development as well. So it's most going to be one of the early deployments. Another location that's kind of looking, that's considering that is going to be Singapore. And potentially there's folks, Melbourne was very interested. At one point, they were going to be the second deployment for Uber after LA, but then Dallas is very interested as well. As you can imagine, knowing Texas and the way the Dallas-Fort Worth area is sort of very spread out. There were some developers who were interested in kind of tying this in with some of their development. So there's, COVID has set things, the agenda back somewhat, but ultimately, I don't think it's going to go away. So better be prepared and have the tools for it. As far as I'm concerned, still fascinated that there's a fundamental diagram in the sky.
With that, I think ending two thoughts. One thing is that this is truly as a parallel with the urban traffic. Before, it's more scheduled system like trains and the commercial airlines, but now it's a truly 4-dimensional traffic, traffic for this case. The others, I was wondering, we already have a bimodal system in the US for short ranges, cars, trucks, cars, and then transit. For long range is the airplanes. With that, I wonder, we'll ever see a day for high-speed rail? Because there's no. Yeah. All right. Well, thank again for.
Thank you.